Since 1 o'clock. Are we ready to start? Yeah, why not? Good afternoon, everybody. Thanks for coming today. I'm here today from the US, and I'm going to go over the BWRX-300 small modular reactor. I have slides for about 1 hour, but I think we have a lot of time for questions and answers. So feel free to raise your hand and we can take questions as we go. But who am I? My name is Christer Dahlgren, and I have worked for GE for 15 years. Before then, I worked at another nuclear plant in the US called Palisades Nuclear Plant, where I was a senior reactor operator. I was born in Sweden. I moved to the US when I was 25 years old, and I've worked and studied it over there since then. I'm one of the co-inventors, and I'm now the chief consulting engineer for GE on this project. So I have been basically in the room from the beginning when it comes to this plant. And I've worked on both pressurized water reactors and boiling water reactors, and also on sodium reactors with GE and pressurized water reactors before GE. So let's get into it. And thanks for coming today, everyone. So we're going to talk about the BWR and the BWRX-300 technology. First of all, what is a boiling water reactor? Basically, it's the simplest way to make steam out of nuclear power. So we have something in common with wood-burning plants. We burn pellets, but the pellets are made from uranium dioxide, and they sit in tubes. And so basically, in the boiler, which is on the left, I have a button here. Yeah, look at that. And we basically boil water using nuclear heat instead of burn heat. So it's a very energy-dense form of energy, so we don't need much volume to create the heat that we need. And so you basically take water, boil it, dry it, separate it, put it into a turbine that spins, that generates electricity. The leftover steam/water gets basically condensed in vacuum and then pumped back into the vessel again. So this is a very traditional equipment on this side, and the boiler is where all the nuclear fun stuff happens. So I'll talk a lot about the systems inside of this containment today, and just a little bit about this because it's very traditional. Turbine generator, condenser is in every plant. So this is very similar to a gas plant or a coal plant that you would already have in Estonia. But this is the unique part. The light water, we have light water, so regular water in this system, and it's used to cool the core because it's a heat exchanger. It generates heat, so we have to remove that heat using this water. But it's also used to slow down the neutrons, which we call moderator. So it moderates the energy of the neutrons, slows it down, because we are a reactor that relies on slow neutrons for fissions. We use low enriched uranium oxide fuel in metal cladding. So you've also heard about pressurized water reactors. So I just wanted to draw the contrast. Here we have a direct cycle, and here we have what we call an indirect cycle, or two loops. So the pressurized water reactor has water going in circles in here that's not allowed to boil, and then they have steam generators. And then we put steam into a turbine, condenser, and feed water. So this portion is identical, but it takes more equipment to make the steam happen in a pressurized water reactor than it does in a boiling water reactor. So we call it the simplest way to make steam. One key thing about this is that it's inherently very stable and very safe because of the void coefficient. So when you increase power in this plant, the amount of steam goes up, which makes the slowdown of moderator neutrons much worse because there's less water particles to hit, hydrogen to hit. So it's a very self-regulating plant, a very strong negative feedback. You have a negative feedback here as well, but since we don't allow the water to boil, it's less negative, so to speak. This one is very, very strong negative feedback. Okay, so that's just kind of like setting the stage for what plant it is. So we just wanted to quickly see here that GE is not new to this. We've actually started working in fission and nuclear physics in the 40s and 50s for the US government. We've worked, and then we started doing civilian nuclear plants for energy and electricity in the 50s, 60s, and 70s since then. And we've basically continuously, since 1960, 57, we've been continuously working on nuclear, either in the construction phase, operation phase, startup phase, or decommissioning phase. So we have a lot of experience in nuclear energy. And we have a fuel facility where I work in Wilmington, North Carolina. So we make the fuel for oil and water reactors where I work, basically. So let's talk about our product strategy over time. As you can see here, here's the different product lines that GE has basically designed over time. And you can see that we have this drive to make the primary or the boilers simpler. We're starting out with very complex boilers arrangement with a lot of recirc lines and even a steam drum in the first plant. Got rid of the steam drum. We still had some extra tanks, and then we got rid of those, and we had just recirc lines. We got rid of, this is 6 recirc lines to 2 recirc lines, 2 recirc lines to no recirc lines. This is the design that's been built in Sweden and Finland the most. The ABWR-like reactors with internal recirc pumps. The external recirc pump plants in Sweden have been decommissioned. So this is the type of plant that our neighbors in Finland and Sweden have right now, but not GE designed, but very similar. And then we went even a step further to get rid of the internal recirc pumps. So now we rely on no recirc pumps. We only rely on natural circulation. And as you can see, the first plant that we built in the 50s was called Ballesteros. And it was set up for both forced circulation and natural circulation. And we have a product line. We've designed plants on the natural circulation side and on the forced circulation side. And now we are just deciding, we're designing BWRX-300. And over time, simplification has been one of our driving forces. And you can see that we've basically eliminated a lot of different systems along the way. But we try to maintain safety or make it safer. Actually, simplifying the system makes it safer because you have fewer possible initiating events if you have less equipment that can break. So now we're at BWRX-300. I'll go over some of the features of it. So it's our 10th reactor. That's where this X comes from. We basically took the last plant that we designed, which was ESBWR. I talked a little bit about this on Wednesday, but it's a very, very large plant, 1,500 megawatt electric. And it's too big for many, many of our potential customers. And it takes a very long time to build. But it is licensed, and we have a lot of design features that we can leverage for the BWRX-300. We've made it smaller, and we also have used a design-to-cost approach, which is where we typically design systems. We get a pushback or a feedback from our value engineering and cost estimators to propose changes that could be better, easier to install, cheaper to build, cheaper to buy, and also look at finding it from the best available supplier as well. Our goal is to have a significant capital cost reduction on a megawatt basis, so per megawatt generated, but still maintain world-class safety. The plant is able to load follow, and it's really ideal for electric generation and also industrial application, for instance, hydrogen or district heat. We have had constructors on the design team since basically the beginning. So we've made sure that whatever we design can also be constructed and operated in the field. We have initiated licensing in the US and Canada, and actually also we've started in the UK and also in Poland. Our goal is to be operational by 2028. And you may have seen the news that we have a contract in place with Canada to actually build this in Darlington, outside of Toronto. So it's 300 megawatt electric, water-cooled. I'll talk about some of these things later, but we've designed it to mitigate LOCA. We've designed it to be able to reduce staff.
What is LOCA?
Sorry, great question. Loss of coolant accident, which means a pipe break inside containment. Thank you for that clarification. And we are trying to be competitive on a levelized cost of electricity basis, LCOE. Okay, so first of all, simplicity drives cost reduction, but also safety increase. So ESBWR, you can see all the systems that the ESBWR had. Lots of pools of water, lots of valves, lots of piping. Because it relied on it had a different safety case for loss of coolant accident. And by inventing and thinking and coming up with a water inventory preservation strategy for loss of coolant accidents and isolation strategy for other accidents, we came up with this simplified safety approach for BWRX-300. And by doing that, we weren't really driving towards reducing the piping. We were really driving to reduce the concrete that needed to hold all the piping and pools. Because the cost of a nuclear construction and the duration of a nuclear construction is tied to amount of concrete and how much concrete you have to put in the ground. So if you look at our projects, we have to really be careful about planning how the concrete construction happens and drive basically improvements to schedule and cost through the amount of concrete. It's not about the metal pieces, it's really about the buildings that the metal pieces sit in. So if you look at the difference between these two safety concepts, you can see that this one needs a lot less concrete. So how did we get there? So we always talk about simplicity. You know, it's not always easy to make it simpler because you have to prove your safety case with less equipment and use the equipment differently. And from the beginning, we started looking at an IEA approach for defense in depth in this plant, where we basically divided in the equipment in different defense lines. These defense lines are basically driven by functional requirements and fundamental safety functions. So every plant, if you run a nuclear plant, you have to think about reactivity control. So that's the neutronics, making sure you can make the plant subcritical and shut it off. That's number one. That's the most important safety function. So that's one fundamental safety function is reactivity control. That's the most important one. If you can take care of reactivity control, all the other safety functions are easy to handle. So it has to work, reactivity control. Number two is decay heat removal. So remove the heat. A nuclear plant generates heat after it's shut down because of the fission products in the fuel. So when you look at coal and gas, you shut the plant off, it's off. Here you still have heat you have to remove. And that's really one of the key differences here, is that we need post-accident, post-event, or post-shutdown, you need to remove heat. And we have several systems that can remove that heat. Then the third thing you have to think about is containing the radioactive material, making sure it's not released, and making sure you have locked the fission barriers down so they don't leak. So that's containment of radioactive material. 3 fundamental safety functions. Now those are then driven into functional requirements. For instance, for reactivity control, we can do an hydraulic scram, or we can do a motor-driven scram, or motor-driven shutdown. So we have different functions for each fundamental safety function. So we align all functions in different defense lines. So defense line 1 is really that we use very high standards and conservative decision-making in the design of a nuclear plant. So we set operating points and design pressures and design versus safety limits in a very conservative way. And we also make sure we have high reliability components so we don't have so many events because the components work well. That's defense line 1. Defense line 2 is our normal operating control systems. So for instance, level control in the reactor vessel, pressure control of the reactor vessel, and then power control of the reactor core. Defense line 3 is our safety systems. So in case the defense line 2 operating system cannot keep the plant running within the operating envelope, defense line 3 will come in and basically shut the plant down. Defense line 4 alpha is our backup shutdown in case something goes wrong in defense line 3. It can also shut down the plant. And defense line 4 bravo is basically the types of systems you need for the unknown events that you haven't thought about from the beginning to make sure that your risk numbers go down, because you can always use those systems to accommodate anything that you may have exceeded in these defense lines. So a typical system here would be fire trucks connecting water to the plant, maybe backup charging of batteries, things like that. And then defense line 5 is emergency response type of equipment, meteorological measurements, dose measurements to make sure that you're not releasing anything, communication equipment to talk to people, both from the government and other officials if something has happened on the site, and making sure that people are aware and know what to do if you have an event. But these defense lines are all here to prevent that from happening in the first place. And our goal is that we don't have any emergency actions for the public. We have emergency actions for the site, but not for the public. So let me go through one example to explain, for instance. We have a feed water level system. It keeps the level in the reactor vessel constant. It has 2 pumps. One is running and one in standby. So you're running the plant at 100% power, and for some reason, the pump trips. So the level will start lowering. The standby pump sees that pump trip because it looks at the discharge pressure, and it starts. That start of a standby pump is our defense line 2 function. So start standby pump, and that will bring level back up to normal, and you can continue to run the plant and repair the other pump. So that's defense line 2. But let's say, same scenario, you have 1 pump running, 1 in standby, this trips, and this pump doesn't start because something has gone wrong with it, or it can't see the discharge pressure, or the computer system doesn't work, or something like that. Eventually, the reactor level will hit a low set point, and defense line 3 will shut the reactor down, scram the reactor, and isolate feed water because something is wrong. So the backup to defense line 2 is basically defense line 3 in that case. So let's say defense line 3 here is using a completely different sets of sensors. This is looking at discharge pressure of the pump, whereas reactor, Defense Line 3 looks at reactor vessel level, completely different. It doesn't know why the level is low. It just acts on low level. And then if that doesn't work, we have a backup system that will also shut the plant down on level or other indications that are separate from the Defense Line 3. So we have basically, this is how nuclear engineers think. We have 2 or 3 ways of basically accomplishing the safety objective. Because we have to have very high reliability on these systems to meet these requirements that is set on the technology by the public. We need to have a very thorough way of thinking through this. Okay. Any questions so far? By the way, this is for the US. If you grew up in the US, this is new to us. And so it's taken a culture shift at GE to accomplish this thinking. But it's really helped. When you look at using defense in depth from the beginning and being conscious about it from the beginning has really helped this plant meet the safety goals. So we have these rules that if we have, depending on the event frequency, the postulated initiating event, how frequent that is. So a pump trip is very frequent, whereas an earthquake is very infrequent. So it depends on the event that happens. We set up rules about we have to have at least 2 functional lines that operate for different event frequencies, and it just depends on what the initial event, if it's 2 and 3 or 3 and 4 alpha. Plus 4 Bravo, of course. So we have layers of safety. In addition to that, we also set up our accident analysis in a graded approach, and we have created this fault evaluation database that basically lists all the event sequences and all the credited functions. And we work with deterministic safety analysis, which is basically running thermohydraulic codes to see if we meet safety acceptance criteria, and also something called probabilistic safety analysis, where you run all kinds of, it's like a event sequence. You look at all the event sequences that can possibly happen, and you see which ones are real, and you bring that back into our safety analysis. So that we can, by doing both of those, we establish a very thorough set of sequences that can impact the core damage, can create core damage. And then by defining those functional requirements, we link those to defense lines. So that way we assure that any event sequence that comes in from the left here is covered by the functional requirements that we've set up. Then those functions, so scram the reactor vessel, is allocated to systems. So in this case, for instance, if you want to scram the reactor or insert control rods on low level, you need to measure a level. So you give that to the reactor vessel system. And you have to insert control rods. You give that function to the control rod system. But then they know I know I have to measure level, but why? Yeah, because you have a safety class, you have a Defense Line 3 function to scram on low level. Okay, that's safety related. That's really important that gets done right. So everybody, by having this system in place, the system engineer that gets the functional requirement to measure level, he can easily go back here, or he can ask too, or she. But typically, this is very transparent and open to everybody. They know why that indicator is there and what's the safety pedigree of that indicator and why they have to have it in their system. Okay. So this is one of the inventions that was part of this plant, which helped. It actually increases the safety of the plant, in my opinion, because what we do, if we have a pipe break on one of the pipes inside containment, we can isolate it using this valve, and or actually these double valves. And it does introduce this concept of preserving inventory in the vessel. Of course, if you want to remove decay heat, it's important to have water in the vessel. If you don't have water, there's nothing to transfer the heat to. If you're into heat transfer, you know that water is a really good it's a really good heat absorber and a really good heat transfer media. It's the reason we use water in all the radiators and so on, at least we used to. It's a very good heat transfer. It takes up a lot of heat and can hold a lot of heat, but it can also remove a lot of heat, especially when it's two-phase flow. It's a very good medium for that. And so we want to preserve the inventory in the vessel. There's already a lot of water in the vessel. We want to keep it in there. So we added these valves. In our past plants, we've had the opposite approach. So when you have a LOCA in a boiling water reactor today, we would depressurize it as much as possible to be able to pump the water back in. But here, we isolate, keep the water in the vessel, and then depressurize using a heat exchanger. So it's a different approach than before. So the second key to safety is this system. It's called the isolation condenser system. And it basically takes steam from the top of the reactor, brings it into this heat exchanger, which then sits in a pool, and the pool is basically boiling off, and steam goes out the building, or out. Now that's not, that steam is not the same as this steam. It's two different sets, right? There's reactor water on the inside of this system, and then there's a pool water on the outside. So this system can be used to remove decay heat very effectively because it takes the steam and turns it into water. But it preserves the inventory, that preserves the water in the reactor vessel. It just removes the heat from it. And it fails in service, and it starts on various signals. But this is really the key to the inventory preservation system. So you isolate, and then you use this system. And they're sized to depressurize the reactor vessel. And when you depressurize the reactor vessel, the driving force for pipe breaks and leaks goes away. Right? There's no push on the water coming out. So it basically equalizes the pressure inside the containment and the reactor vessel. It can also run without any power whatsoever. There's no pumps in the system. So once it's in service, it stays in service for a very long time. And we've sized the pools that these heat exchangers sit in to last for 7 days. So for 7 days, you don't need power, and you really don't need to do anything. You can basically, you shouldn't walk away, but you don't have to operate the plant. It will sit in this state for 7 days and even longer, depending on how many of these are in service. So you see that each loop has its own connections, steam line and condensate return line. And you can see that each loop has a condensate return valve actuation system that are two valves in parallel. They're basically coming off of two different defense lines and two different computer systems, and they operate these valves independently. They also fail in service if you lose power to these valves. They will basically open using a spring. One of these loops is capable of removing all the decay heat of the core. So we have 3 because of redundancy and failure modes. So this is just going over kind of like what happens. So that's the normal configuration. You see the yellow lines are steam lines to the turbine, and the blue lines are that feed water coming back into the reactor vessel, if you remember the first picture I showed, the simplified diagram. So this is basically the normal configuration of the reactor if you're running it at power.
Just a clarification to the people. How tall is the reactor? What are the dimensions?
Oh, that reactor is about 26 meters tall. It's not that small. It's smallish. Smaller.
So that vessel is
Just to give you a point of reference at power, when you're running this plant, their water level sits 12 meters above the core. And we trip it about 4 meters above the core. So we have a lot of margin to the top of the core in this plant. Lots of inventory in the reactor at time 0. It has like a built-in lots of water. I think, hopefully I'll show it later, otherwise I'll draw it on the whiteboard. So you see, this is what happens. So now we're going to trip the turbine. Okay, so when we trip the turbine, that means the steam lines here, the yellow, will basically isolate, right? So you have no place to put the steam anymore. So you need to put the heat somewhere. So let's see if that works. Okay, hopefully this is supposed to, I thought Marty, you helped me with this. It's supposed to play through, I think it's, okay, no, it's just going over the rest of the equipment. Yeah, we need to look at this too. Isolation condenser, steam line, and condensate return line. These isolation valves are normally open, always open, and these are closed. So what we're going to see on the next animation, I hope it's the next one, those valves should close when the turbine trips because the steam line is closed off, and then these will open. And they open on high pressure in the reactor vessel. They sense pressure in the reactor vessel high, they open. They would also open if we lost computers and power and everything else, they would just open. But in this case, they will open on high pressure. So right now, there's actually steam pressure on this system and liquid in this line, right? That's normally how it's operated. It sees the reactor pressure. So it's not going to see some kind of pressurization trend. It's going to sit where it normally is, and it's just going to drain that line of water, and that's going to be replaced with steam. But let's see if it, nope, it works so good. Sorry about that. I'm going to try to poke it. Is it running now? Okay. I'm sorry about that. That should be shown a little differently. But so these valves close, and feed water valves close, and there's no more steam and feed water flow going into the reactor. Instead, we isolate the reactor, and then we put these isolation condensers in service. The name of it, isolation condenser, it is to condense steam in an isolated condition is what they do. The function is in the name. So now, that heat exchanger, we also scram the reactor on that signal. On the turbine trip signal, we scram the reactor, or on high pressure in the reactor vessel, we scram the reactor. So now we're removing the K heat through these heat exchangers. Steam is going up to the heat exchanger, and water is coming back into the reactor vessel. And this is just showing one loop, but all three loops are available.
How much water is there in the system?
Several thousand cubic meters. So I think it's 4,000 or 5,000 cubic meters. I can't remember the exact number. It's a lot of water.
And it's supposed to be enough for 7 days?
It's actually, I've been looking into this very closely. It's enough for, if all three loops are in service, it's much more than 7 days. We've been very conservative when we said 7 days. If you look at the inventory we have up there, it's more than 7 days. Go ahead.
What is the temperature of the steam before the steam turbine operation?
250, 60 C. And it's a 70 bar pressure. Any other questions? And I'm going to go back real quick here and just show you the pool configuration again. So that's just showing one of these heat exchangers, and we have these three. We have inner and outer pools. The outer pools are there for several reasons, mostly to make sure all the pools don't drain from something happening from the outside hitting the building. They're really there to prevent draining all the pools, but they also provide extra water to the system over time.
If I may, you mentioned that you scram
The control rods.
control rods, right, simultaneously. So is it, well, but if you are unable to, is that also a possibility that
So the system can accommodate that event as well, but that's, I mean, we have several means of inserting the rods, and we have a very granular. I'll go through a little bit later, but we've eliminated that to the best of our ability. It's still in the realm of what we analyzed, and we have analyzed that event. Yeah. So one thing we really like about this is that everything we have in that boiler, where we boil the steam using nuclear heat, we've built before. Going from the bottom, from the control rod drives, the control blades themselves, the fuel, the portion above the fuel called the chimney, the steam separators, the dryers, the reactor pressure vessel itself are all based on known technology. And we've built these components before using this size reactor. This reactor is really built on a Swiss plant called KKM, Kärnkraftwerk Mühleberg. And that was shut down just 2 years ago, but it ran since 1972. And the core, for instance, is basically the same core. Same size core, same number of control rods, same fuel. So we know how to operate this plant, and we know how to refuel and maintain this plant. So let's talk about the reactor vessel. When we look at this, if you're interested in boiling water reactors or have studied them before, you'll see that this one is different in two ways. It has no pumps, like I mentioned in the beginning, and it has this thing called a chimney. This chimney is really our pump. It's just a big steam volume on top of the core. And what that does is that it basically provides the thermal driving head for natural circulation. The gravity difference times the height, that's the first term in the Bernoulli equation, if you know that one. I don't know how technical you are, but it's delta rho GH. That is basically the driver of flow through this core. So basically this height here basically makes a manometer effect. So the water on the outside will want to go down here to balance out this manometer. And then it hits this core. The core is a heat exchanger with kind of like a restricting lots of area, of surface area for the fuel, right? So it's a pressure drop. So you basically balance the pressure drop in this core with this chimney height. So that's our pump. Has no moving parts and requires a lot less maintenance and, of course, no power to operate. We also made the downcomer, which we call the downcomer is this outside area with solid water, subcooled water, wider compared to previous plants. It's basically the same width as our previous plants, but since the plant is smaller, there's a lot more area in that outside region. So this water column is very large. So we have a lot of water in the vessel when we run. Like I said, when we operate this plant, the water level here is roughly at this level, and roughly at this level, and we're basically operating at 12 meters above the top of the active fuel. 12 meters is pretty tall. So that's how. So basically, natural circulation just is basically driven by. Actually, it's driven by two things: the height of water here, but also power. Because the more two-phase flow you generate, the bigger is the delta rho, the delta difference, right? The more void fraction you have at core exit, the more the flow wants to go through the core. So it's linked. Core power and flow is linked. So we can't control power using flow. We control core power using control rods in and out. So that's a difference from when if you go and talk to our neighbor countries that have boiling water reactors. They would control power with flow and rods, and we can only use rods. So control rod blades, they're cruciform, looks like a plus sign basically, and they have all these little rods in them and a handle and a little socket to attach them to the drive, and they sit throughout the core. Each control rod blade is used to control 4 fuel assemblies. We use boron carbide or hafnium rods, depending on the location and the demand it will see. We are able to shuffle control rods, especially if we use them a lot. We can shuffle them either out or move them to a different location in the core and replace them. That's normal outage work. Yes? Yes, for the tubes, but it depends. In this case, this is an absorbing. For fuel, zirconium is used because we don't want to absorb neutrons from the fuel. But this one is all about absorption. So it's not as important to use zirconium here because we actually want to absorb neutrons. This is how we control the leakage term in the four-factor formula, right? So we pull this in and out, and we balance the neutron population by adding control rods. So we don't care. Zirconium is not needed in the control rods because we want to absorb neutrons. Go ahead.
I've got a quick question. Well, I know that usually boron are not used in pressurized water reactors, but in case of some kind of emergency, in this kind of reactor, can we use boron to shut down?
We have a boron injection system. Yep. Any other questions? Good question. Yes, go ahead.
Sorry, I have very technical questions. What is used to start the fission?
In the first time, you mean?
First time.
We do. Yeah, you have to add a source the first time, and that's californium-241. We usually put in 3, I think. I think there would be like 1, 2, 3. We would have 3 sources the first cycle, then we would take them out and put them in the spent fuel pool, maybe use then unit 2. Yeah. Yeah, save it for later. But we only need it the first time. The second time, the neutrons are still there from the cycle before. So we use the neutrons we have from the previous cycle fuel. That's a good question, though. You need neutrons to get going. It's not going to go by itself because the new fuel has no radioactivity. You can touch it, right? When you get it from the factory, it's not active at all. It's stable. It gets unstable once it sees the neutrons. So I could have a pellet in my pocket. I don't have one, but I used to. I used to have one on a keychain, a uranium pellet. So I don't have it anymore. Lost it. Okay. The control rod blades, again, are driven by this thing. It basically has, oh yeah, I'm going to talk about that. This is a little bit out of order, I'm sorry. It has this device called the hydraulic control unit. This unit is used to push in a lot of water at a very high pressure to drive the rods in very fast. And we also have a motor on each drive that can drive the rods in. So I'm going to explain how that works now. Yeah, go ahead. Yeah.
Example.
There you go.
You can send it around.
Oh, nice.
Explain first and
Whose is it, so we know to get back to the right person? Okay, this is a fuel pellet, very nice. And one of these pellets is the same as a metric ton of coal. So, do you want to see it? You can pass it around, but it has to come up front here. No, taking it home.
This pellet covers the electricity need for one family
Yep.
for 1 year.
Yep.
For 1 year.
And
for
so
one
the
family.
fuel is 3.5 meters tall with like pencil-like rods, and those pellets are stacked in those rods. And we have about 90 in each assembly, and we have 240 of those assemblies in the core. Thank you for bringing that show and tell. I should have brought one. I have one at home. Control rod drives, very important. We have 2 ways of driving rods. So you can see we have this green, we call it a drive nut, and it sits on basically a drive here that's connected to a motor. We can rotate this ball screw, which basically drives the nut up and down. And this purple piece is what the rod sits on, and that goes up and down basically because it's attached or it's sitting on top. So it's just moving up and down the rod by moving the motor in and out. We use a servo motor here, so it's a very precise, fine positioning. There's no like start up and go, and then it doesn't really stop when you want to. It starts and stops when you want to. So it's very precise positioning possible. Then if you have a hydraulic run, if you need a hydraulic scram, you need to run in very fast. We have these accumulators. The valve here will open, same as the isolation condenser. It also fails open on loss of power. This is fail safe. It will then open and basically release high pressure water into this drive, which will push the rod up using hydraulic force. And then we have latching mechanisms along the way so it can't fall out. And on the same signal that made this water go, we also run the rods in behind it. So it goes up fast, and the rods come in behind it, and then basically locks it in place, inserted. It works without the rod run-in, but the rod run-in makes sure it gets all the way in, and also makes sure it can't fall out again, in case something would fail mechanically in the drive. So we have motor run-in and hydraulic insertion.
Are they identical for the bigger reactors, or
Yeah,
these are unique?
this is identical, and each of these are connected to 2 rods. Right, so we have 1 hydraulic control unit per 2 control rods in the core. That's different. Some designs have up to 8 or 10 on 1 hydraulic drive. It just depends. But we have 2. And we've designed the core so that one of these can fail and the core will still be shut down with margin. And like you said, we don't have to add any boron to shut the reactor down. That is only used for very defense in depth, deep defense in depth. And it's not credited in safety analysis either. Okay, so then I wanted to talk about, I've talked about reactivity control and decay heat removal. Let's talk a little bit about containment of radioactive material. We need something called a containment. And what is a containment? It is basically a fission product barrier. And if you look at a reactor, we have several fission product barriers. The fuel itself, the pellet that you're passing around, is actually a boundary. The cladding, which is the tube that it sits in. Then the reactor coolant vessel itself, the one that we isolate, that's a fission boundary. And then finally the containment, which is a secondary pressure boundary. So we basically have this volume that the reactor sits in. In case we have a break in here, we need to isolate this volume and make sure nothing comes out of this. In this plant, it's underground. The ground level, mostly underground. The ground level is where I'm indicating here. It sits mostly underground. It's combined of concrete and steel. And we have a leak-tight, basically interior steel liner. So it is a pressure vessel. It's just very large. Lower pressure, of course, than this. So instead of 70 bar, this one would be about 4 or 5 bar pressure vessel. But it's still a pressure vessel using ASME pressure vessel codes, just like here, there's also an ASME pressure vessel code boundary. Yes? It is about 34 meters. If you think about it, it's underground really for a few reasons. First of all, we wanted a really stable building for seismic. So the lower the center of gravity is in a building, the less it shakes during a seismic event. And if you have it on top, you need to still design it for the seismic event, and you just need to use a lot more material if it's not in underground to make it stable, because it shakes so much. So that was number one. And then there's another reason for external events. If you can imagine things basically colliding with the building or getting hit, if this building gets hit, we want to protect the containment. So by having it underground, it's protected from those types of events. It also makes it easier to add water to these pools that are up top if you need to after 7 days, because you don't have to pump up so high. So there are many reasons we did it this way. You can see that the reactor vessel sits inside the primary containment. And you can also see that the reactor vessel has basically supports in the reactor building, in the containment as well. So it's supported in here. Okay. So like I said, we use proven technology. For a lot of things. Basically, most of the things you see in this building have been used in other reactors. And that has helped us really put this together, concept together faster. I'm not going to list everything on these slides, but. And you can see that the turbine building, the turbine equipment, condenser, feed pumps are basically identical with some modification of the high pressure steam because it's different, but it's identical to combined gas plants, combined cycle gas plants, 300 megawatt electric. And there's many, many of those that have used this type of equipment. So we try to use catalog items. I don't want, engineers, sometimes they come up with this special thing that they need, and we always make them pick the next best thing that can actually be bought. So that's what design to cost is in our case. Make sure you can buy the thing you're specifying. And this is a more detailed view of the steam cycle. And you can see that steam goes into a high pressure turbine through a moisture separator reheater into 2 turbines, condenser, condensate pump, full flow condensate filter, and demineralizer. Steam jet air ejector is you have to continuously remove non-condensable gases from the condenser to maintain vacuum. And in this plant, since it's connected to the reactor, it can have radioactive material, so we have to bring it through what we call an off-gas system, which is basically a filtering system and hold-up system to make sure we don't release any radioactivity to the environment. Heat exchangers, feed water heaters, feed water pumps, more heaters, and then into the vessel. Cold water joins water from the separators and dryers here, goes into the core, gets boiled. There's a steam-water mixture in the chimney, and then steam is separated and dried and then goes to the turbine again. The biggest difference here is that this pressure turbine, high pressure turbine, sees saturated steam. We don't have superheat like we do in a coal plant or a gas plant. So the biggest modification is this high pressure turbine is just set up a little differently than it would be in a coal plant or a gas plant. This is another view of the steam line and where we take steam. We take steam to all kinds of places in the reactor building, or in the turbine building, I'm sorry. I think I talked about all these things already. One thing that I didn't mention is we use extraction steam from the turbine to preheat feed water, but that's very similar to any Rankine cycle plant. We do that in all power plants. Okay, I want to talk a little bit about construction methods because that's another key innovation to make this plant. One of the key learnings from the big projects, as you've seen in the news about Olkiluoto 3, and we were building AP1000 in the US, it starts taking 10, 15 years to complete the nuclear project. And so if I'm the guy signing, yeah, we're going to do this thing, by the time it's done, I've retired. And some other guy is like, yeah, hey, congratulations, you got my job, and here's this hole in the ground, and in 10 years it's going to generate electricity. It's like not many people want to sign up to a contract like that. It's very hard, especially when political views shifts and even in a company, your strategy can shift over 10, 15 years. So we have to bring the product cycle down to 4 or 5 years or something like that, much smaller. So actually, we have done it. If you look at the Japanese ABWRs, the construction cycle for them were 3 to 4 years long, consistently, on time, on budget, and consistent. And the reasons it was different is not because we were trying to get faster and faster. It was because some of these were built where there's wintry conditions, and we couldn't do certain things in the winter. And also, certain companies wanted to spend less per year, so they extended the construction period to have a fewer staff on the construction site. So it was practical reasons that this schedule was different than this schedule. It wasn't that this went better than that, or this went better than that. It was planned this way. So what you have to do is you have to plan it, and then you have to execute the plan. Being ahead of schedule is better than being behind, but it's not good. You need to be on schedule. You need to stay with the plan. But we have done it. And as far as this is concerned, we're focusing on this building in the middle, which is the safety building, reactor building, where all the safety systems are, where the boiler is, where the containment is. And we're looking at it basically with the same mindset that we did the ABWRs. What chunks, so to speak, what portions of this building can you build together and then lower into the hole without distracting work, so you can parallel work. Put work in parallel if you don't have to make everything, you don't have to work everything, as I call it, inside the hole. If you can work outside the hole and then bring it in, what efficiency gains can we make? And we came up with a construction method that relies on steel and concrete composite material. And that's configured in a special way that you can use the same exact building, but you can actually make the parts of the building different depending on where you build it and how you can transport those parts to that construction site. So the logistics of making everything show up on site is very important in terms of how big you can lift, for instance, how many tons, what crane do you have, and how big can that crane be? Do you have rail, barge, or truck? There's a lot of factors that go into this decision. But by doing this, it's almost like Lego, because the individual pieces are the same. It's just where the cuts are that's different. And so we basically do what we call minimum excavation hole. And then we lower in these pieces in whatever configuration we find is the best one, and stack the building up from the bottom up. So the two key innovations here was the method that we put together the structure using the composite concrete material, and then this minimum excavation. Usually in nuclear construction, you basically do maximum excavation, and then you flow back with really good material. For instance, one of the projects we looked at, the dirt on site was bad, quote unquote bad, so we took it all out and we flowed in concrete to fill back up, which is very, very expensive. And it takes an extremely long time to move millions of cubic yards or meters of dirt and then replace it with new dirt that you had to import, let's say, from Finland. I don't know, that's the craziness that I've heard about. So instead of that, we've done a lot of work to justify this minimum excavation approach, a deep hole basically, and then stack up the building on top of the bottom, from bottom to top. And that saved a lot of time and a lot of expense. Okay, so that's all I had to cover. I think I'm right on time. And if you have any questions from that, please let me know. Yeah, go ahead.
In case of some kind of catastrophic failure, like in Fukushima, what about hydrogen?
Yeah, let's go over the Fukushima event. How many here have heard of Fukushima? So yeah, good. So then I don't have to go over what happened. We had a seismic event and was followed by, what happened after the seismic event? No, what happened before hydrogen, after seismic? But what happened before? What was it like? Well, to the site, what happened in Japan? seismic event, tsunami, ding, 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 that's the word I'm looking for. The flooding, right? So seismic event happened, flooding event happened a few minutes afterwards, 50 minutes afterwards. Seismic event, everything was fine. Flooding, we lost all electricity. And that plant relied on electricity for a lot of its functions. Like for decay heat removal, they needed pumps to do decay heat removal. In this plant, we don't need electricity to do decay heat removal. I think that's the key difference here. We also don't need the water in the ocean to remove decay heat in this plant because it's in the reactor building. Now, if we have hydrogen, it won't be as a result of a Fukushima event, but it could be something else. It would then collect in the reactor building because we vent the containment in that kind of event to the refuel building, to refueling area, and we're putting passive autolytic recombiners in that area. Any other questions? Yeah, go ahead.
Common to build these types of plants underground?
We have done it in the past. It is new. We always had portions of the reactor building underground.
Okay.
But the way we're building that hole is new, or not new in the world, but new to nuclear.
During the first slides, you mentioned that you removed the core catcher from the
No, I removed the core catcher we used in ESBWR. It's not as complicated as the one in the ESBWR. The reason being, this is a much smaller core, and we have a lot more area, so we allow for a spreadable area with the refractory material, but we don't need an active we don't need the same type of core catcher that we use for ESBWR. Good catch. I mean, no pun intended, but that was a good question. Yep. Anything else?
I have some question about reactivity controls, controlling, because, well, boiling reactor has some issues about that. For example, as I know, with different heat, because of the different temperature and boiling bubbles will be different neutron still, so it will cause different reactivity on different heat, so...
Different where?
Because, well, the temperature of the water on the bottom is less than on the top of the...
No, it's all the same basic. Well, it's a little bit subcooled going into the core, but we're keeping the reactor vessel at saturated conditions, which is, it's a straight line on your steam diagram. You're basically, TS diagram, it's a straight line, so you basically have the same temperature whether you're liquid, solid, or gas, or steam. It's the same temperature. It's just where on that straight line you are. So the temperature is not different in the reactor vessel. It's actually very stable, and it's a little bit subcooled, maybe 10, 15 degrees subcooled at the bottom, but other than that, the whole vessel sees the same temperature because you're saturated. So remember, its TS diagram is like this, and we're just on this line right here, and the T is the same T across. It doesn't matter where you are. When you start to boil water on the pot, and when you basically boil like crazy, it's the same temperature on your stove.
So the neutron field are pretty equal on top.
Neutrons, now that's a different question. So the neutrons are not affected by temperature, they're affected by the void. And so the void, if you have more steam than water, you have less moderation.
Exactly.
But it's actually really good to have that feature, because if the void fraction goes up for some reason, if you lose pressure or if power goes up, moderation will be less and power will be less, because you're basically going subcritical. So it's an extremely self-regulating effect, very, very good self-regulating effect. I don't know if I answered your question, though. You said something about activation, or maybe I didn't hear you right, so sorry. Okay. Does that explain it, or?
Yeah.
Mm-hmm. Yeah, go ahead.
Do all these implications make the plant easier to operate, or is it harder for the reactor operator?
My opinion, it's easier, because the post-accident actions, there's fewer pieces of equipment to monitor and determine status of, and there's nothing to do. Now, it's almost too little to do. Like, you have nothing to do for 7 days. What are you going to do then? Like, you're gonna you know, if you're an operator, I was an operator for 4 years, and you never sat around like this. You always try to do something, right? So I think the challenge here will be to make sure the operators know enough about the plant to trust it, and then try to plan for the right things to do instead of trying to interject into the accident, let it go, but then plan for the post-accident conditions that you need at 3 to 7 days. Like, get the pumping equipment ready if you need to add water, you know, get the backup chargers in place if you need that type of thing, instead of trying to adjust reactor parameters during the accident. So it'll be interesting. I can just tell you that where I worked, we had to do 20 manual actions within the first 20 minutes of the event. So it was like we had 2 people just going around checking stuff, making sure they were in manual or whatever it was, you know. And here we have nothing to do other than post-SCRAM. You would verify equipment configuration and that you're in safe operating condition, and then you would sit down and start writing the report, what happened, kind of thing. Yeah. It'll be interesting to see how when the training program gets going and how this is to train the operators to trust the machine. Yep, go ahead.
How do you control the reactor power since low power, low power? How do you go down from 100% to 90% to 50%?
Okay, so that's a good question. In this plant, pressure control is done by the turbine control valve. So it's throttling flow to keep the pressure constant in the reactor vessel. So you can't just change the valve position here, because that's going to change the pressure, and then it's going to go back. So what you have to do is first you have to set the core power at your new demand signal. And then when core power, let's say you go from 100 to 90% power, you lower core power here, the pressure is going to stop dropping because the flow lowered. And then this one will close, and that will admit less flow to the turbine.
And how do you lower the
Rods, control rods, the insert control rods. And then you withdraw control rods again to get the 100% power. Pressure will be too high. This one will open as a result, and you have the power you need to the turbine. So the reactor drives the turbine, not the other way around.
Does it take?
No time. No. We can't go up super fast. It's a direct response, so we have to be careful. You could go up very fast, but we have to protect the cladding around the fuel pellet. So we don't go faster than 0.5% per minute. 2 minutes per percent of power. So in 15 minutes or so, 20 minutes, you could go up to 100% from 90%. We just don't want to, not structure so much, but we don't want to mess with the heat transfer and thermal fatigue on the pellet, the tube that the pellet sits in. And we're extra cautious. I mean, we don't want to mess with that. Because if you have problems, you have to shut down and replace that fuel assembly or run with a control rod permanently inserted, which will not help your fuel economy. So we try to be extremely careful.
How often do you need to reload the fuel?
So it depends on your operating strategy, whether you're 100% power all the time or whether you want to load follow. But we've designed the reactor to be between 12 and 24 month refueling cycle. Right. So we have, I think I showed it, but I didn't really talk about it. There's a spent fuel pool in the reactor building that can hold 8 years worth of fuel. And once 8 years have passed, I think you can see it here, you have to basically put the fuel into a cask. You take the cask out and you put the cask somewhere, or you make use of an interim storage facility. Like in Sweden, they have something called CLAB, C-L-A-B, and they have a place in Olkiluoto where they put fuel in a pool for 40 years, and then they do deep geological repository after that.
How many fuel bundles will the plant burn over the 60?
If it's 1 year, we have to do some math here. We start with 240, And then it's 36 per year. So you'll find out in a second what it is. I'm not doing it. A few thousand, a couple thousand? More than that, 4,000. Just guessing. 8,000. What did you come up with?
What about military threats?
Yeah, so the reactor building is built for that. It's built for, I can't talk too much about it here, but I would say any bad guy scenario you can imagine, including very large things and also very small things. So, and that's all I'm going to say since we're recording.
But you said that the operator mustn't, it's good if he does nothing about the 7 days or at least some hours, but if the operator really wants to do something bad, can he?
Not really, because of the fail-safe nature of the safety systems. Go ahead.
What is the regular maintenance like? Is it once 2 years?
So there's maintenance you do all the time to repair things, and then
Downtime.
yeah, so then you shut the reactor down for a few days every year or every other year, and it's going to be anything from 8 to 14 days depending on the scenario. Once per every 15 or 20 years you need to do real turbine outage, so that takes a little longer. And once every 10 years you have to do some key measurements on the reactor vessel for service inspection. That takes a little longer, but usually between 8 and 14 days depending on the scope. And the core is very small, so you can refuel it very quickly. The critical path is really the disassembly and the reassembly of the reactor vessels to get to the fuel. And so you take a bunch of pieces out, you get to the fuel, replace it, then you put them back together like one of those dolls, basically. No, it's basically like a stacking operation. Go ahead.
What about maneuvering the power from 100% down to like what is the lowest?
You can't be much lower than 25, I would say. What we've counted on is going from 100 to 50 daily in our thermal fatigue analysis. So that's our design basis scenario, that you go from 100 to 50 on a very frequent basis and back up again. Any other questions?
Yeah, be brave. You can ask.
Yeah.
Because
I'm only here for another 15 minutes.
how many people are operating that?
Okay, so we did some estimations on the minimum staff. You can, of course, add if you want to, but we say about 75 to 80 people. And it's a very operations and security focused workforce. Because
One shift or
no, a total. What?
At a given moment, is it 3 o'clock?
20?
And how many guys are you using?
Well, you can probably do it like at night, like let's say midnight shift, a dozen. 5 operators and some security people.
During daytime, more people than...
Yeah, because you have normal operating staff or support staff training, people like that. It could be even less. So our minimum shift complement total is 4, is what we came up with. So it could be less, but we need some security, some support, maybe chemistry, rad protection, unless we can combine it with operating crew. And some of those are country specific, sorry.
this is when you have one reactor.
Yes, for one reactor. Each reactor in this plant has its own control room and its own staff. Now, if there's possibility for future projects, depending on the situations, to make an adjustment where you can combine certain things like that. For now, we have not combined that. For the standard, it is one control room, one unit. So you're not focused on more than one unit at a time.
There would be 3 shifts per day.
We would do 2 shifts, but you have total 5 or 6 shifts because you have to have time off and training and so on. So typically nuclear plants are run with 5 or 6 shifts. And in this case, we would have 4 people qualified nuclear operators per shift. So 28 to 30 people, something like that, total. Because you also need backup operators and if people get sick. And that was based on a 12-hour per day shift. But you will only work 3 or 4 of those in a row. No, go ahead.
Talking about the plastics, right? You know, where you store the most problematic waste. You said 8 years. Where is it usually stored? Like, I know in Finland they have like those huge storages.
They do. Well, they have 2 things. Yeah.
The ones produced here, like, be transported to Finland, or do you have some kind of waste stored in Estonia?
That's a good question. So I can tell you about Sweden and Finland have a ship, right? And they bring fuel around to the 2 central fuel storage facilities, one in Olkiluoto and one in Oskarshamn in Sweden. And so Estonia, that would be one way of doing it in Estonia. In the US, every plant in the US has these big, huge concrete structures that they sit in on site. So basically, you take out this cask out of the building, and then you put it in a concrete storage facility on a pad. So in the US, we have no repository or it's typical of the US to not be able to figure this out because we can't agree on anything. So we can't agree where to put it. So everybody just keeps it. So hopefully, I don't know. You may know.
I can comment. Currently, international treaties do not allow to take waste and store it in the other countries. So when we produce waste in Estonia, we need to store it according to current treaties. In Finland, yeah, they keep it in big pools for until now 40 years. You know,
Mhm.
pools.
Yeah.
And then it goes underground, deep underground for 500 years. And in the US, it's just containers sitting on the parking lot, like a big.
Well, it's a fancy parking lot. Expensive parking lot.
Expensive parking.
Lots of security and yeah, but that's basically it. Yeah, so there are options, but I didn't know about the international treaty, so that's something we have to work out or figure out. Yeah.
But yeah, we are in Fermi-Energia, we are analyzing different options which are the best options.
Mm-hmm.
What is probability of worst scenario, damaging of reactor core?
Well, so with that defense in depth picture that I showed, since we've built that in from the beginning, we ended up with very few core damaging scenarios. And they're typically in the 10 to the minus 8 to 10 to the minus 9 frequency. So that's 100 million years to a billion years. You still have to do something about it, so we are. But they're low frequency events.
More questions?
If the container building is made from like modules, is it still as safe compared to making it on site?
They're actually, so I should clarify. The steel is made off-site, brought to site, put together, and then we flow the concrete into the steel structure on-site. And so, but I don't think it matters if it's made off-site or on-site, as long as it meets quality requirements and meets the specifications. It shouldn't matter in terms of how safe it is. It's just a matter really of where you spend the money and where you can have people and how much you can bring in that's already made. There's an argument to be made that factory-made equipment has a better ability to do a repeatable process than in the field, because in the field, different weather conditions and, maybe like tough, like you have to lay down and do the weld or something. So that's an argument that you can say that it's actually better to make it off-site and then put it together on-site. But overall, no matter where you make it, you have to meet that specification in order for you to call it safe in the first place. And we make sure we do that. So. Make sense? Okay.
Okay, I see no more.
Yep, there's one here.
Yeah.
How much waste is such a reactor create?
Radiologic waste.
Yeah.
So there isn't all that much. We have what's called a liquid rad waste system, but it's really a liquid recycling system. So the waste that we will create is that the mineralizers have these beads, anion and cation beads in them to make the water clean. Those beads, once they get full or make saturated, that's really the waste products. Water, we don't have any water waste because we reuse the water. There's a little bit of waste generated in an off-gas system because there can be some radioactivity going through there. So like charcoal filters, media and so on gets spent and we make waste out of there. But it's not, that's really what it consists of, and a few cubic meters per year maybe. So not a lot. And that's also very country specific because in the US we might have different rules, so we can concentrate it more and make less. But if you have different rules, then we have to have more but less radioactive. It just depends on where we can put it and what the rules are in the country that we operate in. And we can adjust for it in that design.
Seems that we can conclude the lesson here. On behalf of Fermi Energia, big thank you, Christer, because he actually came to Estonia only because of this lecture. So big
Thank you. Thank you.
And yeah, as a Fermi Energia, we chose this technology. We announced it this Wednesday, so we'll be in close cooperation with the Hitachi knowledgeable team. We have already people gone to your trainings, 1-week trainings
Yep.
in the training centers, and there will be a lot of opportunities, and we'll be sending students and trainees to Hitachi to work, and
That'd be nice.
it's interesting times ahead. So if you're interested in nuclear, so come and talk to us and come to the modern nuclear technology class, which was yesterday. Annette Marie can tell more if there's some people who are not in that class yet. So thank you very
Yep,
much.
thank you. Thanks for reminding me.
coming, everyone.
Thank you. Okay, good. Thanks. Thank you. Yep. I have 3 microphones on. I'll let him take care. Thanks for coming.